Okay, let me really start by thanking the organizers especially for organizing this great conference in this complicated situation. Yeah, so I will, actually, let's just get started. Okay, I don't need to tell this crowd about the incredible richness of ecosystems and anything from the number of species, chemicals exchange, survival strategies, species associations. We've heard these things even in the last few days. If you look at the literature, though, in ecology, you see a lot of theories that actually try to do something and say, well, maybe it's not that complicated after all. For example, neutral theory, maybe, there are 700 species of flowering plants, but maybe it's all just one flower and the different colors don't really affect anything that we should care about. Similar related question is, well, maybe a network of different species in some field can be simplified into just 2 or 3 species, one flower, one butterfly, and so on. Another type of simplification we see a lot, and we've heard even in this conference, is what I call here single axis or maybe a few axis. So for example, a niche type of description where you have here in this graph over here, in this figure over here, you see different birds, and they just live in different parts of the tree, and that's what allows them to coexist. Trade-offs between, for example, species that have more offsprings and those that invest more in a single offspring, and so on. Going to another type of simplification, if you look at dynamics, so here you can see dynamics here it's an example of phytoplankton in some lake, and then you can ask yourself, well, is what we're seeing due to fluctuations in external conditions, for example, or is it due to some internal mechanism that's driving these dynamics? And generally the question we want to ask is, how do we identify and understand ecological communities that are not one of these types of simpler descriptions? We'll call these high dimensional theories and high dimensional dynamics and so on. Okay, so there are quite a few different fingerprints, characterizations that we have been pursuing, we and other people in the field, for what it would mean to have these high dimensional, high diversity communities. I want to focus on one, and this is what I'll be calling the diffuse interaction patterns, looking at the interactions between species and looking for some of these fingerprints. All right, so just to be more concrete, let me put us in a specific setting. So first of all, I'll be only discussing ecological dynamics. In that I mean that I won't be talking about any evolution. And so the simplest setting is you have S species, and they have relative abundances N for each species, N1, N2, and so on up to S. And by relative, I mean abundance divided by the carrying capacity. And then, for example, we can choose some dynamics, let's say the Lotka-Volterra dynamics, which I assume you've seen before. Why Lotka-Volterra, not other things? Well, first of all, it's just an example here. It's a popular type of equation people use, and also it turns out to fit nicely to the data I'll be showing you later. The important point here is that if you look at this equation, you see this matrix alpha here, which gives you all the pair interactions between species. And the point is that there's a lot of numbers, lots of parameters there. So if we have, I don't know, 50 species, then we have easily over 2,000 numbers there, and we have to somehow deal with that situation. And finally, I'll only, in this talk, I'll only be discussing equilibrium, namely the system has reached a stable fixed point and the abundances do not change anymore in time. All right. So the basic idea here is that perhaps we can replace this high dimensional, the interactions in a high dimensional setting with some random interactions. So what you see on the right is what you would get if you look at a case where you have one interaction mechanism. This is this matrix alpha on the right for a specific, this is the competition colonization mechanism by Levins and others from the 70s. But maybe if you have many things happening together, there's no conspicuous order, and you can take these numbers, as I said, as random. And again, in my talk, I won't be adding any additional structures such as trophic structure or functional groups and so on. I refer you to Mathieu Berlier's talk tomorrow. He will be talking about these things. All right, so okay, so you can say, let's say that the interactions are random, but can we actually do something? Can we actually look at interactions and say, well, are they what we would call random-like, or are they more something like these low-dimensional descriptions? Well, there are a few issues with doing that, but I think perhaps the most basic zeroth order issue here is that a fully random interaction matrix, and by that I mean that all these numbers, all these alphas of the interactions are completely independent. Such an interaction matrix does not allow all the species to coexist. So if you run the dynamics I was just describing before, what you will find is that some of the species will go extinct and only a subset will survive. And so there's only a, so not all of them can survive, and then the matrix of the surviving species is a different matrix. All right. So what I want to say now is to ask, well, what are the conditions for coexistence? So again, going back to the dynamics I mentioned before, these Lotka-Volterra dynamics. So if I say, okay, a species has reached a fixed point, its abundance no longer fluctuates, then you see that there's this equation here that has to be equal to 0. And if the species has not gone extinct, then this n in red is larger than 0. And then this, what's here in these parentheses has to be equal to 0. And so full coexistence, if I have some set of, let's say, 8 species, and I know they coexist, what that means is that there's this thing in the parenthesis has to be 0 for each of these species. And so that is translated to a matrix equation. So the matrix alpha of these interactions times the abundance vector n is equal to a vector that is all ones, 1, 1, 1. And of course, when you invert this, you better get positive numbers here. And that's why this is a hard, question. Why, under what conditions do you get these set of positive numbers, and what can you say about that? All right, so so the idea is the following. What we want to do is the following. Suppose that we are given the abundances of the species, right? We measure and we go to the field, we measure and we see a set of abundances for the species. Then we know that if this Lotka-Volterra equation holds, that this constraint, this matrix constraint has to be satisfied. But note that there's still much freedom in the matrix alpha. So I only fixed here actually S, just a number of constraints is the same as the number of species. And still this matrix alpha has many more entries. So the idea is to do the following, is to say, well, okay, let's just take all the matrices that do admit, all the interaction networks that do admit this vector of abundances as a solution. Okay, so you have here, you see in this gray circle, you see all the possible matrices. Most of them do not have this, do not give these abundances. And then there's a small subset, and we only want to look at that small subset. And What that means mathematically is that we look at the conditional probability distribution. So if I say I have a prior distribution on these alphas, I say, well, I don't know anything about them. Let's assume that they're independent random numbers. Well, what happens once I condition on this matrix equation? So I get a new conditional distribution. And if the prior distribution are these IID random variables, I can actually calculate this posterior distribution. It's a rather straightforward problem in probability theory. And let me tell you the answer. Let me tell you what we get. So what you see is that the conditioned matrix, or the conditioned distribution of the matrices, is no longer these independent random numbers as before. So one thing you see is that the matrix is composed of a completely random matrix as before, plus a shift in the means of the matrix. So if you see here on the right, it's a sum of some underlying pattern that shifts the means of these different numbers. Okay, so some interactions are on average stronger, more competitive, or less competitive. And the pattern, okay, you can see an equation for it, but verbally, what we can say about it is the following idea. Pairs of successful species, pairs of species that are able to live together with high abundance, interact less competitively. So they don't compete as much with each other. So if you like, it's some kind of, I don't know, some mafia behavior. You know, the successful ones look out for each other and don't compete as much. And so a successful species is one that biases its competition. It fights less with the other strong species and more with the weaker species, while the unsuccessful species are just fighting everyone in an unbiased way. They don't choose their competitors in any biased way. So they're not specialized, if you like. It looks like the successful species are specialized. And then there's another piece of this probability distribution with correlations. I don't want to get into it in the interest of time. All right, so just to summarize this more theoretical part, so this pattern that I just mentioned, so by construction, it guarantees that a matrix that has this pattern will lead with the dynamics to abundances to species having positive abundances, so species coexist. The interpretation, as I mentioned, is that of pairs of successful species interacting less competitively. And finally, it's what we call diffuse. So it's many, many small shifts underlying under something that looks very heterogeneous and random, quote unquote. It's hard to tell the difference by eye between two matrices of interactions, one where species do coexist and the other where they don't, okay? So if you don't know what to look for, you might not see this, okay? So it might be out there and you just don't notice. Okay, so now I want to go from models to data, and I want to present our analysis of a specific experiment. So I want to present one experiment, and it is one of many, many experiments of plant biodiversity experiments. And these experiments are essentially ones where you take some set of species and you grow different subsets of these species together in plots, and you measure biomass. So this is the Wageningen biodiversity experiment. It was run for 12 years. It had 8 species of plants that grow naturally outside in the area where the experiment was carried out in the Netherlands. In total, it's a very thorough experiment. They had over 100 plots of species with subsets of the 8 species they chose, all monocultures, pairs of species, different subsets of 4 species, and all 8 species together. They tried to maintain conditions as close to natural as possible. For example, there wasn't any watering of the plants. As I said, 12 years. And one interesting thing is that it happens that in the plots that contained all species, all 8 species managed to coexist for the duration of 12 years. And it seemed in most experiments that, once we looked at the data, it looked like really species abundances reach some fixed value and fluctuate over it for most of the years. Okay, and above ground biomass was measured once a year, and that's the data that we are using. All right, so what did we do with this data? So the first thing we did is we tried to fit this fixed point, this equilibrium Lotka-Volterra model to the data. And by that, I mean that you fit this matrix alpha. And how do you do that? Well, you use, it's enough that you have monocultures and duocultures. So the 1 species and the 2 species data for 2 plants, and that already gives you the interactions between them. And because this, there were so many, there were 80% of the duocultures were actually done. We had a lot of data from that as well. If you add the 4 species plots, then really you can get the whole matrix, and you can check, and it happens, and this is an empirical fact, that actually the Lotka-Volterra model here fits very well and reproduces the 8 species coexistence abundances very well. We did quite a few statistical tests to see that this thing holds. I won't get into that, but we do think that in this specific case, the Lotka-Volterra model is a good model for this case. All right, but now what I want to do is go back and look at this matrix and try to understand what we see here from the perspective of the model that I was describing before. And so this matrix here is already ordered by this relative abundance. Again, I remind you, a relative yield, which is the biomass at coexistence when they all grow in the same plot, divided by the carrying capacity when each species grows alone. So it's already ordered from the smallest abundance to the largest one. And okay, we look at this matrix, and I don't know, I already see patterns here because I've been staring at it so much, but maybe it doesn't look like much to you. And so what I want to do is I want to take here in yellow the effect of the species that are the least abundant. That's the yellow two leftmost columns, and see how they compete with other species, and do the same for the top 2 species here. Okay, so this is just a quick look at the data. And what we expect is, I remind you, that the very abundant species will choose their competitors, will compete less with other species. And indeed, if you plot the data, you see this very clearly. Okay, so the most successful species do not compete less with other successful species. That's the green points here. You see this clear trend, whereas for the unsuccessful species, for those with low abundances, you do not see any trend in the data. Okay, they compete with everyone more or less equally. All right, we can do this quantitatively per species. By the way, these are species you all know from your day-to-day life. This Leo here is the oxeye daisy, okay, that I'm sure you recognize. So anyway, so we do this plot of the slopes of the different columns of this matrix. And what you see is this clear trend towards larger slopes, which is precisely this more specialized, this more of a mafia behavior, or fighting less against other successful species. And not only is the qualitative trend there, but in fact, we have a quantitative agreement with the theory. Remember, the theory says that only the abundances of the 8 species together give you information about these slopes. There's a quantitative fit with theory, and this is a fit with no free parameters. Okay, this is so the agreement here is at least as far as this measure goes, this looks almost like I generated the data in my computer synthetically. Okay, even the variation around the the expected behavior is the same as it would be expected in theory. So really no species here looks like it's deviating dramatically from this null behavior. Okay, there are other ways. In the interest of time, we tried a few other ways of slicing and dicing and looking at these interaction coefficients in light of this model. Some sort of moving average that again fits excellently. Again, I won't get into that. Just two short final comments. One is that there's another way to derive this pattern. And in fact, that's how I stumbled upon it originally. And that is to say, well, I start with many species and I let the dynamics run. I do an assembly process. I see who survives and I look at the matrix of those that manage to survive together. And it turns out it gives exactly the same theoretical pattern. And the other thing is, for those of you who wonder, because usually these random matrices are discussed in, due to, in the context of linear stability in ecology, this has nothing to do with linear stability. So if you're worried about May bounds and so on, this is not affected, nor does it affect the linear stability of the matrix. All right, and I'll close here, just quickly summarize. We assumed interactions are this maximally random, but we need to allow for coexistence. We get a theoretical pattern where successful species avoid competing with each other, and we validated these things with this pattern. We saw it in plant biodiversity experiments, more than one. I showed you just one example. To look forward, we think of this as a null model for interactions between species that is a non-neutral model. You can add structure. You can ask what other types of dynamics might lead to this, this final result. And again, Mathieu Barbier tomorrow will discuss more these implications. So yeah, I think I'll close here. Thanks.